This is an oral history interview with Rafi Nave in Haifa, Israel. Rafi, thank you very much for joining me. It's August 28th, 2025. I'm Jerome Coonen in Palo Alto, California.
Oh, I'm delighted to be here, and I would be love to share with you both the story of the early days of Intel in Israel, as well as specifically of the 8087 Math processor. Go ahead.
Well, that's great. Well, to get started, why don't you tell us a little bit about yourself and the early influences that got you into a high-tech leadership role at a young age?
Well, I was born on December 20th, 1949, and I would like to give a little background both about the country as well as later on about my family, as it influenced my childhood and whatever happened afterwards. Um, as you may know, the state of Israel was born on May 14th, 1948, like a year and a half before I was born. And actually, the first 10 months or so were the independence wars. So, in practice, the country was less than a year rolling before was born. And in all fairness, the first 10 years were really, really challenging for the country because after a year of, war with no economy running, as well as the fact that within the next 3 to 4 years, over 1 million Jews immigrated into Israel, both from Europe, survivors from the Holocaust, as well as from the Arab countries where they were not wanted anymore there. Basically, you had here a country that doubled or over than doubled its population, and had to live with almost no income, whatever. So the whole country was very, very poor. I guess if I don't know if they did any GDP analysis at the time, but if they did, then Israel was in a very, very, very poor shape. Now, specifically about my family, my father and my mother both were uh, growing up in Europe, mid Europe, if you may say. If it were not for World War II, then both of them would have had very successful careers in Germany and Austria, where they were born. But as it turned out, because of the war, they had to escape, and their life changed terribly. So I'll start with my father. My father, his name was Joseph, formerly in Hebrew, but Lothar was what everybody was calling him. He grew up in a city called Graz, which is the second largest city of Austria in the southeast corner. Um, and when he was 23 years old, it was the Anschluss. The Anschluss was when the Germans pretty much annexed Austria, and that was on March 12th, 1938. And that very day, he ran away and escaped. Luckily enough, very close distance, like a 1 hour drive, was Maribor, which is a city in Slovenia, and he crossed the border to there. And from there was one of his uncles. He proceeded to Trieste in Italy, and from there he boarded a ship and came to Israel. So he arrived in Israel with pretty much nothing on him. So he was a refugee and came to a country that couldn't offer him much. So it was a non-promising start for him. My mother, she was 17 years old at the time. I'm talking now about 1938. And she joined a youth movement that is related to Zionism. And with them, she arrived in Israel also in 1938, and again without anything. And now I need to go back a little to my grandparents because they are party to this whole scheme. My grandfather, from the side of my father, he was a very successful merchant in Austria, and he dealt with textile. He was selling those fabrics for furnitures, for curtains, for God knows what, both in his store in Graz as well as across the country. Actually, his claim to fame was that he imported the first car into Austria. So that was in the early 20s. Already he had a car, and at the time, there was no driver license, no training, whatever, but he used it in order to distribute his merchandise. And also, my father learned how to drive when he was very, very young already. And they, had good time until the Nazis arrived. And then, like 6 months after the Anschluss, Adolf Eichmann came into Graz, and my grandfather was considered the leader of the congregation in Graz. So he called him into the office and said, "Hey, by the end of the week, I want a list of 1,000 names of people who are going to be relocated to some military factories in Germany. Go do it." And he argued and argued and they couldn't reconcile, but he gave him a day to think about it. And people told him that evening, if you do not escape tonight, that's the end of it. I mean, you're going to be jailed and probably you're not going to see daylight again. So my grandfather and grandmother, again, crossed the border to Maribor, and within 2 weeks they were in Israel, again with nothing. So despite the fact that they left behind them tremendous wealth, they could not take any of that with them. Also, we need to understand that they came to a country where they didn't understand the language or anything. So it was a very poor start for them as well. Regarding my grandfather, from the side of my mother, namely her father, he was a rabbi. His name was Rabbi Zigbert Neufeld, and he was what is called a liberal rabbi. He was a student of Leo Beck, if you heard of him. And he was the leader of a congregation in a town called Elbing. Today it's called Elmborn, which is in Poland today. At the time it was East Prussia, not far from Gdansk and not far from Kaliningrad. And again, they led very great life. Maybe a curiosity is the fact that in World War I, he was serving as a rabbi in the German army. He was actually a German officer in the German army. And as a result, he got honors and so on. But again, in 1938, they believed everything was fine and, life is going to be okay and so on, until what is called the Kristallnacht, the night where there were tremendous, activities against the Jews by the Nazis. And he realized that it's not going to be a good future. So they escaped Germany as well and came to Israel, again, with nothing on there. That's roughly the background of the family before we go into myself and my childhood. So the early start then for my family was not that great, but in all fairness, that was the situation for almost everybody around. All our neighbors and so on were all what you may call lower middle class. So they had little income relatively and could make a living, by working hard and so on. But specifically, I want to go back to my father. As we said, both his father and mother arrived in 1938, and before long, the World War started. And he enlisted into the British Army. You know that there was this campaign in North Africa, Egypt and Libya and so on, where Field Marshal Montgomery was fighting against Rommel. And my father was there for about 5 years in the British Army. And since he had the skill of driving from early life, then he became a truck driver there with those British soldiers. And when he left the army, actually, the British Army, actually, he had already three things that worked for him. First one is, as we said, the fact that he was a very skilled driver. Second one was command of English, because for 5 years he was in the British Army. And the third one, which was interesting, was that in the last year or so, okay, he was already stationed in Israel, and from time to or in Palestine, as it was called at the time, and from time to time, some senior British officers would come to do some sightseeing, to see the holy places and so on, and he was volunteered to take them and show them around. And in all fairness, initially he could drive and show them, but he couldn't tell them much about it because he didn't know. But he realized that he needs to know that. So he borrowed or bought some books and spent the nights learning about the holy places and about any other interesting attractions in Israel. And it turned out that he basically was a de facto tourist guide when he left the British Army. When the State of Israel was established, about a couple of years afterwards, in 1951, they did the first course of formal tourist guides, and he was one of the three only graduates of that class who were formally endorsed as being an authorized tourist guide. So he's one of the first three tourist guides in the State of Israel. And actually, he made a living of that for the next 50 years. Okay. My mother, she was, as I said, 17 when they arrived. Initially, they gave her all sorts of agricultural assignments, to grow vegetables, to feed chickens, and so on and so forth. But before long, she went to a training of sewing, dressmaking, and so on, and that became her skill. So eventually, she became a dressmaker or a tailor for ladies. Eventually they found the way they could make a living. The problem was that on top of themselves, they also needed to take care of their parents because the parents came with nothing and they had to support them. So it was a pretty heavy economical burden on them. That's roughly the background. I'm not going to dwell in deeper unless you want to hear more. Now let me go about myself. As I said, I was born at the end of 1949, and 13 months later, my brother, Michael, or Mickey, was born. And since we were so relatively short time apart, we were growing up almost as twins. And for all my childhood, basically, we were the two of us together doing everything. Actually, the family was not in great shape, but we didn't feel that. I mean, we had a very, very happy childhood, I must say, and enjoyed, the freedom it also gave us. For instance, let's take when we were already, let's say, 7, 8, 9 years old, okay? We would come back from school, eat lunch, do homework for an hour, and then for about 4 or 5 hours, we would go down to the street. By the way, streets there were not with concrete. They were still with gravel or with sand, okay? And there we would play with the neighbors, okay? For instance, there were some yards that weren't yet built, so we fixed some goalposts there from bricks and played our football, which is in the Americans call soccer, okay, and so on and so forth. So we had very, I'd say, enjoyable and happy childhood in that sense. We also learned how to accommodate new friends because every now and then a new child came to the neighborhood either an immigrant or somebody who moved from an apartment and so on. And immediately you need to make friends with them. We had all sorts of projects that we initiated of building things or, planning things and so on and so forth. So I'd say that all in all, our childhood also gave us the skills of the things that you don't learn at school, but rather you do them naturally with your age group. So when I'm trying to summarize my childhood, I would say it was very happy, not rich, but who cares because nobody was rich there at the time. And it gave me some very useful skills that later on helped me in life. So
How was school for you, Rafi?
and school, it turned out school was very easy. Oh, that's an important point. My parents, they emphasized one thing, studies, because both of them could not complete their own studies at their homeland because of the World War. Okay, they wanted to make sure that their children are going to complete studies in the best form that they could, and because of that, they made it very clear to us that studies is very, very important. Okay, and I mean, I can say that it came natural, but I never missed a day at school. Same about my brother. Namely, we attended school fully, even if you had some fever or sore throats or whatever. That's not a good enough reason not to go to school. So we were very adamant about that of, attending school. Also, I always came with homework. And this is maybe an interesting observation. Everybody almost in my class, and I guess in other classes as well, would prepare the homework the night before it's due. I would always prepare the homework the day I got it. Okay, so in some cases it was a week before it was due. Already I completed my homework. I don't know which one is better or not, but it made sure that I always have my homework ready when I come to school. And we took school seriously, and it wasn't hard. Namely, we didn't need help or anything. Our parents were too busy making ends meet, so they couldn't help us with homework, but it wasn't necessary. Another interesting just comment is my grandparents, okay, did not command Hebrew. My parents did, but my grandparents on both sides did not. And because of that, we had to practice some German. Okay, with them we talk German, so we also sort of acquired an extra foreign language, German, that day to day. Okay, I cannot read a scientific article in German, but I can converse and get by with day-to-day German. Yes.
So at home, you spoke Hebrew and German and English, all three?
No, English we did not talk at home. We talked Hebrew and at home, and with the grandparents, we talked German. English, interesting point. My father, as I said, was a tourist guide. And from very early time, I used to join him in tours. And there I had a chance to talk with tourists English, okay? Because he was guiding in five languages, okay, German and French and Italian and German. But as I said, a lot of it was English. So I learned some basic English from the age of 6 or 7 years old already because of those tourists.
Very good. Did any subjects at school appeal to you more than others?
Oh yeah, definitely. Oh, another interesting point. When I started second grade, okay, we started learning Bible. So my parents bought me a Bible, a full Bible. It's the Old Testament from cover to cover, from Genesis all the way to Chronicles. And I used to read it like you read, a fiction or a regular book. So I would read a chapter a day, something like that. I don't know if you know, but the Old Bible, the Old Testament has 929 chapters. So over 3 years or so, I would, go through a full cycle of reading every single chapter, and I enjoyed it. When I look at it now, I can't understand. I could enjoy it because some of it is interesting, but a lot of it is boring or whatever. But somehow I did that. Also, I read a lot. We were subscribing into a library, and I could borrow books. So I borrowed and read about 2 books every week. Okay, so the fun of reading was there. And maybe an interesting twist to that is the day I enlisted to the army, I decided during the 3 years of the army, I'm going to read only in English. So during those 3 years, wherever I had time to read, I had a couple of English books and so on. So I read probably during the army something like 100 books or something like that during those 3 years. And all of them in English, which improved tremendously my command of the language.
When did you enter the army?
Pardon?
When did you enter the army? Was that after high school?
At the age of 18, when I graduated from high school, this is when most Israelis go to the army.
Right.
Back to your question about subject that I liked. So I loved Bible, as you may have guessed, and history and literature and so on. So everybody was sure that I'm going to be, a humanistic scholar or something of that kind. Interestingly enough, when I started 10th grade, okay, that very year, the municipality of Tel Aviv did an experiment, and to the 3 leading high schools, they started a program of studying electronics. Okay, despite the fact that they were humanistic, high school, they had this electronics program, and to me it sounded curious. So what happened was that I enlisted to that. And that changed my career or changed my life because for the sake of it, for 3 years, I studied English. Studied electronics, okay? And I graduated with a matriculation with electronics. Furthermore, those people from those 3 high schools were enlisted to the communication regiment or communication corps. And for the 3 years of the army, I was serving as an electrician and so on. So my whole career, rather than being humanistic, got the twist towards electronics. Okay. Naturally, when I finished the army, I went to study at the Technion with most of those who served with me in that program, and I studied electronics. So rather than becoming, professor of literature or of Bible or something like that, I became an engineer of electronics.
Oh, that's very good. So you entered Technion immediately out of the army?
Yes. Actually, even I got released from the army 1 month before because I got accepted to the Technion, and they had this kind of accommodation so that I wouldn't lose a school year. So while I was supposed to be released in November, I was released in October and immediately started studying at Technion in the electrical engineering faculty.
Were there any particular people who influenced you in those early years? Obviously the electronics course had a huge impact. Were there any people who did specifically?
Yeah, but this is part of a broader topic that I would like to spend probably 5 minutes on, and that is how the whole domain of semiconductor came about in the state of Israel, and in that is embedded also the person who influenced me tremendously. So when I describe this to people who are not Israeli, usually I tell them that in Israel, if you want it or not, every decade we have some war. Okay, it starts with 1948 with the Independence War. In 1956, it was the Sinai Campaign. In 1967, it was the Six-Day War. 1973, the Yom Kippur War or the October War, and so on and so forth. Why do I explain that? Because if you go back to the 1956 Sinai Campaign, which is probably the less one that people are familiar with. The one interesting thing about it was that this was the only war where the Israeli army, the IDF, collaborated with the French and the British armies. Okay, the reason was that there were two reasons for starting this war. One was that the Egypt leader, Gamal Abdel Nasser, imposed a blockade on the Eilat Gulf so that no ships could come to Israel from the south. And also, he nationalized the Suez Canal. Now, the Suez Canal was before that led by or managed and run by the British and the French, and they could not accept it. So, Israel and France and Britain sort of changed or divided the tasks so that Israel conquered the Sinai Peninsula and the French and British took over the Suez Canal. Okay, I'm not going to belabor on what happened afterwards, why they were vacated and so on, but interestingly enough, 11 years later, in 1967, okay, was the Six-Day War that you might have heard of. And in that war, actually the first 3 hours were what made it all happen, where the Israeli Air Force annihilated the air forces of Egypt and Syria, on the ground, basically, and that determined the war as a big success for Israel. One side effect was that the president of France, Charles de Gaulle, was very, very upset with Israel that they did not consult with him, they did not ask for his permission, and they went along and did it by themselves, the Israelis, without collaboration with France. So he imposed what is called the embargo. Okay, that was a boycott on any military-related merchandise or equipment or anything going to Israel. By the way, we have a similar talk about it nowadays in a totally different context. But back to then, okay, that was imposed their embargo. So one interesting thing that happened then, you might have heard of the Cherbourg boats. These were 5 destroyers that Israel bought from France. They paid fully for them, but they were held captive because of the boycott. And then in the night of Christmas of 1969, those boats, when everybody was drunk in the harbor, they escaped and they came to Israel and so on. Since they were fully paid, there was no legal issue with that they got to Israel. But the other thing was, if you think about it, the reason we won the Six-Day War was the Air Force. And the Air Force was fully French airplanes, those Mirage from Dassault, the Mirage 3 and Mirage 5. So getting spare parts for those Mirages was critical for maintaining the Israeli Air Force. So 2 things happened. One was Israel established a factory for engines. Okay, it's called Menoi Bet Shemesh, and the primary thing was to build spare engines for those airplanes. The other thing is, when you think about it, when you have air-to-air combat, one of your critical things is that you will recognize the enemy airplane before they recognize you. And the way to do that is by using some infrared detectors, okay, that could go as far as 5 or 6 kilometers, okay? But we had no technology for those detectors because they were built from materials that, if you know the Mendeleev table, from the 3-5 combinations, such as gallium arsenide, indium antimonide, and others. So they didn't know what to do. And here I come to my mentor, a professor at the Technion, okay, Professor Yitzhak Kidron, came to the management of the Technion and to the management of the armament authorities and told them, guys, give me 2 years, give me, I don't know, $5 million, whatever it is, and we'll have a lab that could build you as many detectors as you want. And they gave him the budget, and he did that. So he started in 1968 and he completed in 1970. In 1970, he could supply as many detectors to the Air Force as was needed. A side effect from that is that they became experts on semiconductor, okay? And they learned how devices work, bipolar devices, MOS devices, and so on, and later on, even how to design integrated circuits. So, for example, when I needed to pick which chains, it was called, of expertise I go, like I could take computers, I could take networks, I could take control or whatever. One of them was semiconductor. And actually I picked that. But just to say, this was a game changer for many other things. And in a minute, I'll talk about that when I talk about Intel. So, yes, what else?
No, that's excellent. So that so that's the path that got you through the Army and communications to toward Intel, where we're about to head through Technion and the sudden expertise in semiconductors. And so you graduated from Technion after the Army, and went out to seek your first employment after school, right?
Yeah, but I would take another break to explain one more thing, and that is how Intel got to Israel, okay? And that has very interesting twists to that. So Intel was founded in 1968. You might have heard of, Gordon Moore and Andy Grove and his name runs me, Bob Noyce. Okay, the three leaders that left Fairchild and built Intel. And about 7, 8 years later, okay, they ran into a challenge how to recruit engineers in the Silicon Valley. It happened to be that one of the leading engineers at Intel at the time was an Israeli called Dov Roman. He did his PhD in UC Berkeley, and afterwards, his claim to fame was that he invented the EEPROM, the erasable programmable read-only memory, and he became very respected in Intel. And he told the management, Andy and Gordon and Bob, he told them, if you look for engineers, there is this place called Haifa in the other end of the world where they are learning semiconductor in the Technion because of this thing that I told you about the detectors and so on. And there is almost no competition on those people. So you can hire and they can work for you as long as you need them. Why don't you try that? And they decided, okay, we're going to try it. And then I was at the time a student at the lab of Professor Kidron. And I saw the sign on the wall that says, Intel is coming to town. If you want to join us, okay, come and interview with us on October 15th. That was in 1973. By the way, we knew very well Andy Grove, not because of his reputation that he later on was, one of the stellar managers and so on, but because he wrote a textbook on MOS transistors. Okay, and we learned from that textbook in our class at the Technion. Anyhow, okay, you know what happened on October 6th that year. Okay, the October War started. So clearly they did not come over, and we were enlisted for 6 months or so. Actually, the Technion was closed for a whole semester and so on. It was very terrible times, but eventually the war finished and we came back. And then back in March, we had another sign on the bulletin board that says, Intel is still coming to town. And we're going to be there April 15th or something like that. Come and interview with us. And I consulted with Professor Kidron. I asked him, look, they are asking for 3 years of experience. I didn't complete my studies yet. I have another semester to go. Should I apply? And he says, what can you lose? Go and apply. Worst case, they will decline you. And I still remember to this day the interview that I went to. It was in the Dan Carmel Hotel in a suite. And they were there, Andy Grove himself, and Leslie Vadez, who was the VP R&D of Intel at the time, and Dov Froman. And for 2 hours, they grilled me. Luckily enough, I brought with me the project material from a project that I did in the lab at Professor Kidron. It's a 4-bit shift register. And this started asking me, why did you place this transistor here? And how did you determine its size? And show me the simulations, and so on and so forth. So it was a pretty demanding interview. 3 weeks later, I got a letter to my home, to my parents' home. At the time, there was no email, no fax, nothing. Okay, so I got a letter, snail mail, that says that I got accepted to Intel. Okay, so and it says, you start working at Intel. Intel will open its gates on July 1st, 1970. We're talking about 1974. So comes the day. By the way, I still didn't complete my studies there at the time because we lost a whole semester in the fall. They had a semester to fill in for it in the summer, so I still had about 2 months to complete my studies. But I came there on July 1st. I come to where the offices were supposed to be. It's a very shabby environment, of metal shops and garages and so on. And there was a sign that says Intel. I come in and nobody's there. 8 o'clock, like deserted area. About 2 hours later, at 10 o'clock or so, Tom Innes, who was sent from the US to become our manager, shows up and he sees me and he starts laughing. So I asked him, why do you laugh? So what do you do here? He says, I told him, they said that today we start working. So I came. Oh, they didn't tell you that we start at 1 p.m. Okay. So the fact is that I am the first employee of Intel in Israel by 5 hours before the other three came. Okay? So could be by mistake, but it was, or by design, whatever you want. So actually, the four first engineers at Intel were Amos Vilnai, I don't know if you heard of him, Asher Kaminker, Yossi Mannheim, and myself. And that's how we started our adventure, I would say, as Intel Design Center in Israel.
Mm-hmm. No, that's a great story. And so you just had the 50th anniversary a year ago,
Right.
in 2024, and so do you want to fast forward to 8087, or do you want to talk about a few things that you did before you got to the 8087?
I just mentioned that not just for myself, but the whole design center at Intel, in Israel of Intel, for the first 3.5 years until the end of 1977, did pretty much interesting projects, but they were like second-class projects. For instance, on the 8080, some of the peripherals, the timer counter, the interrupt controller, the keyboard and display controller, were designed in Israel. Same about the 8085, its peripherals were designed in Haifa. So the perception was that Intel Israel is okay, but it's not, the same class as the Santa Clara Design Center, where all the microprocessors were developed. Okay, so that was the context when the opportunity of the 8087 came about. And it goes like that. First of all, Intel started its third generation of microprocessors. There was in 8-bit. There was 8080, there was 8085, and now they were designing the 8086. And they figured that it should have also a companion chip or a coprocessor, which will do all the arithmetic. It will do the calculations, the 8087. And I'm talking now about early December 1977. Our general manager, Eli Porat, calls me into the office and says, they're designing, or they are conceiving this 8087, and it turns out that nobody wants to implement it. Go to Santa Clara and figure out whether we should consider it. Okay, so I traveled over. I was, by the way, with my earlier project, the keyboard and display controller, I spent a whole year in Santa Clara on its transfer to production. So I knew very well the company. I knew very well the environment there. So it wasn't like a culture shock for me when I came there this time on a trip. So for 2 weeks, I met anybody that I could on this new project, on this 8087. And it turned out that everybody thought it's going to be a very challenging project, but that the chance of it working are very, very low. First of all, it was so complex that it would be 2 to 3 times more complex than the 8086, than the main processor. B, its size would be such that the chance of it yielding more than one die per wafer were slim, so that the chance is that you're not going to find a working die just because of its size. And also, it may not fit into any existing package, and so on and so forth. There were all the arguments. And besides, it was so complex that, there were so many reasons why it may not work. So I understood what it's about, but I didn't realize how really complex it is. And then we had this conference call between Eli Porat and myself to conclude my visit there. And he asked me, okay, so should we take it or not? And I told him, listen, everybody knows it's not going to work. So if it won't work, we just fulfilled their expectations or their assessment. If by chance it works, okay, then we'll gain tremendous respect and tremendous breakthrough on our abilities. Okay, so we decided to take it on. Okay, I mean, I know that there were some people in Santa Clara that, they breathed easier because they said, oh, now it's not off our back now. They have to worry about it there in Israel. Our luck from the side from Santa Clara was the fact that there was a team under John Palmer, okay, who became my best friend, who was Mr. Floating Point, we called him, and him plus Janice Barron plus Darsan Tien. That team, okay, were experts on floating point, and they actually guided us on everything to do with algorithms, with computation, with everything that we needed in order to implement the chip, so that we weren't, on totally, barren ground, in a sense. But we had, a tremendous challenge on our hands.
Can you talk a little bit about what each of those three people did? John and Janice and Darsan?
I don't know the division of labor there, but it was clear that John is the expert, okay? And he is also the contact with, we may talk later about the IEEE 754 committee and so on, with Professor Khan and so on. So he was the expert. And Janice and Darsan were assisting him on all the assignments, okay? An interesting aspect, that's a side story, is Janice was married and she couldn't bring children. Okay, so eventually they decided they're gonna, adopt, and they went through two channels. One was through some lawyer company, and the other one through some church. And within 2 months, they got two babies, one from each channel. And that month, she got pregnant with twins. Okay, so within like 9 months, she had 4 babies. So clearly, she had to leave work and to build her family. So we missed her a lot, but priorities are priorities. So that's all I can tell about the team there.
Right. No, that's very good. So the design, the 8086 itself, the CPU this would attach to came out in 1978. So it wasn't quite shipping yet itself, right? It was still to come.
I think it was in 1979, but could be.
Might have been. So you worked on the 8087 before the CPU was entirely ready, and the design, design was still developing as you worked on it, right?
Yeah, but the handshake between them was fully defined Bruce Ravenel was the architect that designed this um, handshake between the processor and the coprocessor, and that worked very, very well. So it was already implemented on the 8086, it was implemented on the 8088, and from our end, then we did just the other end of the handshake so that it worked fine.
You said you might get one die per wafer. How big were those wafers then?
The wafers were 4-inch. It was a process called 411. And there were 80 die placement on a wafer. But as you said, the projection at the time was half a die per wafer. Luckily enough for us, by the time that we taped out, okay, they improved the manufacturing process so that the defect density got reduced and it became something like 2 dies per wafer.
Right. That interesting. And how often did you visit Santa Clara after you got started?
I came every 4 months or so, and I spent most of my time with John Palmer and his team. Plus, every time I went for at least one day to Berkeley to spend the day with Professor Kahn, because there were a huge list of questions that I needed to get his guidance on how to do them right, on exception handling, on algorithms, on transcendentals, whatever it was. So most of my time was spent with the software and with the algorithm persons.
Mm-hmm. And Khan was a consultant to Intel then?
I don't know if he was formally a consultant, could be, okay? He was worthy, definitely. I mean, his contribution was tremendous, but I don't know what the formal relations were.
Right. But John Palmer was your primary interface.
Definitely. And actually, John and myself worked as a team, almost indivisible team. I mean, anybody who looked from the outside couldn't tell where I finish when he starts and so on, because we were doing everything together, and it was fantastic collaboration.
Uh-huh. Did the Santa Clara people ever come out to Haifa, to your office?
There were, some managers used to come to Haifa, but in all fairness, they didn't care much about the 8087. In their mind, it was a lost case. It's something that, okay, we let the Israeli guys do it to keep them busy, but we don't have high hopes anything is going to come out of it. And they had other more important things to worry about, and that's what they spent their time when they came to Israel. By the way, there were already starting discussions about manufacturing in Israel and so on. So there were other topics.
Right. Well, one more question about Santa Clara, and then we'll go over to Haifa. Did you interact with other projects going on in Santa Clara at the time? Or were you very focused on 8087?
No, almost none. I mean, the 8088, another maybe interesting aspect, the 8-bit derivative of the 8086 called 8088 was also implemented in Israel, and we were lucky to have Rafi Retter, who was a tremendously talented engineer who did single-handedly the 8088, and we inherited him to do the bus interface unit. So he did it for us. This way, the whole handshake with the processor was handled professionally and without any errors and so on, due to Rafi, and we needed less support from Santa Clara because of that. But I don't recall working with any other of the projects.
Right. Well, we'll come back to the 8088 a bit later. But let's go to Haifa. And so you took on this ambitious project, and now you had to build a team, find some people to carry out all this work.
Yeah. Again, I mean, if I were to do it today, probably I would have taken a much larger team. But the team at the time included, in total, only 7 engineers, okay, out of which 3 were experience. Well, when I talk about experience, I talk about 3 years, not 20 years. About 3 or 4 years experience before they joined the team, and the other 3 were new recruits. Okay, these are the engineers. We also had a team of 8 math designers because there was a huge effort of math design that needed to go to implement the chip. So it was a totally, a very lean and mean team, but of very dedicated and talented people. I can say for myself that for the first year and a half, namely since January 1978 when we started till mid 1979 when we taped out, okay, I spent almost 24/7 on this 8087, and on February 20, 1978, my first son, Eyal, was born, and I barely saw him because my real baby was the 8087 during that year and a half. That same applies to most of the team people. They really spend day and night working on it to make sure it works fine.
Mm-hmm. Can you talk a little bit, just a couple of sentences about what it was like to lay out a chip in 1978 and 79?
Yeah.
It was done.
Yeah, as I said, it wasn't the first chip we were doing. So the technology we knew, just a matter of complexity of the subject matter. So we were laying out on Mylar. There was Mylar that we had, lines, marked on it of millimeter, where every millimeter on Mylar would stand for a micron on the chip. Okay, so the math designers would design their polygons on that Mylar. Then we had a system called Calma that we had a digitizer that would put it on the light table and would click on every polygon, and this way you would enter the polygons into the system and eventually built the layout this way, module by module by module, a pretty tedious and challenging process.
Mm-hmm. How big did the die turn out to be for the 8087?
I don't recall by heart, but it was roughly a centimeter square. Okay, namely.
Right. And so you drew a picture of that centimeter 1,000 times larger on both sides,
yes,
right?
Yes. So it would have been something like 10 meters, but it was pieces by pieces. It wasn't a whole thing as one chunk.
Right. And was the technology, the chip technology of the 8087 the same process that was used for 8086 and 8088, which were done at the same time?
Yeah, it was the same process 411, and it was the same CAD technology, namely the layout and everything was using the similar system.
Uh-huh. And let's see, this is a long time ago, so you didn't have email, but you must have been in regular contact with John Palmer and his team in Santa Clara. How did that work? You had a time difference and
actually, the time difference worked for us well. I mean, what happened was that we would work from 8 to 4 or 8 to 5, like normal work day, like everybody. Then I would go home, and the same applies to many of the other engineers, spend time with my children or with my baby and so on. And then roughly at 7 or 8 p.m., we would go on the phone with Santa Clara and sort all the things that are between the two sites. So for them, it was already morning, like our call now that we're talking about. It's slightly after 7 p.m. and it's 9 a.m. your time. So that was roughly the time that we would spend on business between the teams at the time.
Uh-huh. And did you have fax? Did you send images across too?
I don't think so. First of all, images, I mean, there's nobody there who was interested in images, so that was not relevant. But I think that our communication was mostly phone, and telex. Maybe there was already fax, but it would have been used primarily for text,
Yeah,
not
I think
for
that was
pictures.
a tele. So you did, yeah. So it was rather limited communication, mostly voice um,
Yes.
between you. Well, that's
Yeah.
interesting. There are a couple of directions to go here. One is to look at some of the some of the hardest parts of the chip to implement, or the biggest challenges you encountered along the way. Maybe it's time to move to that.
Sure.
You were learning, the arithmetic was developing as you were building the chip, so you were working really in parallel with John Palmer, if I recall correctly. But that seemed to work well.
Maybe, Jerome, maybe it's time to mention the IEEE 754 standard, which, by the way, got
Sure.
also a milestone recognition from the IEEE, because the 8087 was a guinea pig on that standard. It was the first product that would implement the standard in full. And the end result is excellent because the computations are really accurate and reliable and solid. So it was a very noble goal. But to get there, you had to deal with hundreds or maybe thousands of nitty-gritty details on how do you do all sorts of exception handling, how do you do rounding, and how do you implement this and that and so on. How do you deal with with infinities, with not the numbers, with all sorts of other elements that were in the standard. So I needed the handholding of John Palmer and in some cases of Professor Kahn in order to do it right. And in some cases, I gave them the feedback of, hey, here there is a problem. Why don't you consider in the standard to do it this way or that way in order to do it simpler or to do it more reliably? Or here there is a hole in the scheme or something like that. So the collaboration there was critical for both ends in order to get the best results, both on the standard as well as on the 8087.
Mm-hmm. Yes, they were developing at the same time. In 1978, the floating point committee was just getting started itself, and they were not unrelated. But this is your story of the 8087, the 754, which is very important and is very much tied up. Is a story all its own that happened at the same time. You had the 8087 had remarkable properties that surprised many people. It had wider arithmetic values than most people would have expected for that time. And you had a 67-bit data path internally, for example. Maybe we could talk about a few details like those.
Yes, well, as we said, this is a floating point implementation of the mathematics. So it has a mantissa and it has an exponent. The exponent was 15 bits, and the mantissa was as wide as 64 bits. Okay, depends on you later on can trim it or around or do all of those things, but all our computations were done for 64 bits. Plus, it had a tail of 3 more bits called guard, round, and sticky bit that allowed us to accommodate for any bits that are shoved to the left of the number so that we eventually get the most accurate result we could. And actually, for other implementations, such as the transcendental functions, we basically had a data path of 67 bits that we could do the computations on. So it was a very, very accurate computational machine.
Mm-hmm. Well, let's pursue that a little bit just to round that story out. The IEEE standard was influenced very heavily by Intel's work and Professor Kahn's work with you. I worked with him at that time, but that's my story, not yours. but we'll focus here. The standard was all about data types and arithmetic and high quality operations. But you've mentioned transcendental functions. Why don't you talk a little bit about those? They were not part of the IEEE standard, and definitely a top secret. I never knew about them. People on the committee, 754 committee, did not know that Intel was doing this. So you did something way more ambitious. So why don't you talk about the transcendentals a little bit?
Okay, before I do that, I just mentioned that personally, okay, that was the most exciting thing I liked doing because when I learned numerical analysis and so on at the Technion, I loved those, original algorithms for square root and for arctangents and for logarithm and others and so on. That was one of the more exciting parts of of this project beyond all the other challenges. Specifically, again, I don't know who invented the Cordic algorithms. The Cordic stands for coordinate rotations. It's a very interesting way of computing very accurate transcendental functions using some pre-calculated constants that represented factors of 2 to the minus something. I'm not going to go into all the details of that, but as a result of that, you could, in every round of shift and add, get half the resolution and so on and so forth until you get to a remainder which is something like 2 to the minus 16 and so on, and on that you did the actual computation using some approximations and so on. I'm not going to belabor on that. By the way, I wrote at the time a whole paper that was published in some technical publications on that. But basically, we were able to implement the functions that were essential in order to do our computations. Pretty much there was a tangent, arctangent, logarithm, and exponent. And from that, the software library could devise all the trigonometric functions and all those exponential functions that were needed to do arithmetic with very, very high precision and with nice performance.
Yes, it was incredibly ambitious. There were no mainframe computers at the time, or mini computers of the 60s and 70s, who had functions like tangent, arctangent, log, and exponential in hardware. So that it was, it was a remarkable achievement.
Thank you.
And you found a way to fit them right into the way you did multiplication and division, right? I mean, that part of that beauty of that is that they just fit right into the 8087's overall computation scheme. Is that correct?
Yes. I mean, there was this basic concept, or maybe I didn't mention it yet, but first of all, we had a microcode machine, okay, that was exercising like software, all the programs that you wanted in order to implement those things. And it was operating on the data path that has registers, it had adder, it had a shifter, which was a very powerful tool to do some of those algorithms. And with that, we implemented both the fundamental functions, as I mentioned, like multiply, divide, square root, and so on, as well as the transcendental functions. So all of them were very consistent as far as the way they operated due to this microcode engine.
Right. On the committee, when we heard about this work, it was called a barrel shifter, and that was an excellent design within Intel, right? That you were able to leverage for the 8087.
Yes. Interestingly enough, one of the qualities of an MOS transistor is that it's symmetrical. Namely, yes, we call the ends of it gate and source, but you can call the source gate and you can call the gate source. Not gate, sorry, source and drain. Sorry. Okay. And basically, it runs to the right and to the left symmetrically. So we could use that matrix of transistors, in order to shift entities to the right or to the left by one place or by as many places as you wanted. We also divided it into a byte shifter and a bit shifter so that you can do any number between 1 and 63 locations in one clock. So it was very, very useful.
Mm-hmm, mm-hmm. There was also, and part of the shifting had to involve the sticky bit, the rightmost bit. Is it interesting to talk about that for a little bit?
I don't think it's so much related to the shifter. It's related to the fact that if you take, let's say you take two 64-bit numbers and you multiply them, okay, the results is actually 128-bit long, okay, and you cannot represent it in a regular format. So you need somehow to figure what happened with the 64-bit of the tail, okay, and the way to do it had the fact that you needed to remember if any of the bits shift to the right had a 1 in them, okay, that is what you cared about, and that's called the sticky bit. So if at least one out of the, let's say, 62 bits that were shifted out was a 1, then the sticky bit would be a 1. And then you had this garden around that you needed to do something special to know if you are exactly midpoint between two numbers, or you are higher than that or lower than that. And based on that, you would do all sorts of rounding exercises and all that in logic. So that's something we implemented. It was very logical. It was very easy to do once we knew what was expected. And it worked great.
Yeah, we should talk about the microcode a little bit. While we're talking about the transcendentals, these are very sophisticated functions. They required, you mentioned some magic constants, some very unobvious bit by bit constants you needed. Somebody had to compute those, and then somebody had to test that you were implementing your algorithms correctly. You want to talk a little bit about how you got all this right on the chip when it came out?
Okay, so first of all, the constants were computed by John Palmer's team. So either Dar Sancien or a guy called Konrad Ralai, one of them did the computation of those constants for us. Okay, we simply embedded them. Okay, the algorithms, I mean, we had a lot of guidance from Professor Khan and from John, and we implemented it as prescribed, and they worked very, very well. Now, this is the point to mention a guy that if he was not there, the 8087 would have never came out. His name is Yaakov Yaari. He was a software engineer on the team, and he implemented single-handedly a simulator of the whole 8087 in Fortran. Okay, so that eventually we could run any thing from a microcode program. You would implement it and run exactly as the hardware would implement it and get the results to where they need to be in a register or whatever. And eventually we used it to run millions of test cases. You know, we had like a regression suite that every time we had a new version of the microcode, we first of all would run, let's say, 1,000,000 test cases and see that all of those came out right, because it would flag anytime that there was a deviation or something that didn't make sense. And then we would test the new things that we implemented and see that those are doing well. Because of Yaakov, I think or his simulator, we found hundreds of mistakes or hundreds of things that needed to be corrected. And eventually, when the chip came out, it worked the first time. It could not have happened if it were not for Yaakov's simulator. So it was a manna made in heaven, you know, that we got this skilled engineer and the simulator that he gave us.
One more question about that. Of course, we're talking about 1978 and 79 here. You know, the personal computer had barely been invented, but Yaakov is running in Fortran. What computer did he use to run his simulator on? Do you know?
Yeah, our center at the time had two what is called SEL-32 computers. They were actually some kind of leftovers from the Air Force some kind of computer from the US, not from Israel, some kind of real-time computers for aviation something. But for us, they were just general purpose computers. And we could run, Fortran or other things and simulations on those computers. So they were in-house, which was very easy for us. And we don't at the time we weren't personal computers yet. Actually, the first personal computer already needed the 8087 and the 8086. So we did it on those SCL 32 computers.
Yeah, that's a great story. Well, let's talk about the microcode ROM, because that had some fame of its own as well. You had a lot of arithmetic and now transcendental functions. These 4 functions to implement. What happened with the development of all this ROM space?
Before we talk about the ROM space, let's talk about the microcode itself. Okay, it had its own language. Okay, namely, we have our own assembly language for the microcode, which you can do a move, you can do an add, you can do all sorts of that from this register or from that source, and so on and so forth. I mean, it was a real program, and we had a brilliant engineer called Charlie Wymore, who was the owner of the microcode. Now, he was a funny guy. I loved him. And one of the things he heard once, the term in Israel, in Hebrew, that said, kill a Turk and rest. It was something like, you complete a task and then you rest a little. So he decided that he's going to call the revisions of the microcode Turks. So we started with Turk 1 and so on. And at the end of the game, we had Turk something 47 or something like that. So there were about 47 revisions of the microcode, each one of them improving functionality and fixing errors and so on and so forth. So it was handled like a software program that ran on not a general purpose, but on a specific computer. And the testing of it was on the simulator that Yaakov built. Now, all in all, every word in the ROM was 16 bits, okay? And there were total of 16,048 words, okay? So we had 1,648 words of 16 bits. Okay, so if you multiply the numbers, you get something like 25,000 or close to 30,000 bits in the ROM. Okay, and when we calculated, we figured that the ROM will be too big. It will not fit in the die. If we had to implement it that way, the die wouldn't fit in the cavity and probably the yield would be terrible. Luckily enough, we had on our team another very innovative engineer called Moshe Stark, and he had an invention that later on, like 30 years later, companies like SanDisk and M Systems and others were using a similar one, which involved the fact that on every bit location, you can have more than 1 bit. Okay. In our case, it was 2 bits per cell, we called it, namely that on each transistor location, you could put either no transistor or the largest transistor or 2 other sizes and so on. So actually there were 4 combinations, and you had a sensor at the end of the ROM that you could sense what is in that bit. So we could actually on each location have 2 bits stored in the ROM. And this way the ROM was half the size. Instead of being 25,000 or so bits, it was like 13,000 bits. Okay, and that fit were in the area that we could afford.
That's a great story. Did Intel use your 2 bits per transistor design in later chips beyond the 8087?
I think that one of the chips of the 432 system tried to use it. Whether they use it in the end or not, I don't know. But as I mentioned, I've seen this approach being used like 20 years later in the industry, again, to squeeze size.
Right. And so you managed to fit it into a 1 centimeter die. How about, well, I mean, you've talked a lot about Yakov's tremendous contribution with his simulator. You had all the rest of the chip to verify as well. Can we talk a little bit about verification and how you got this whole thing to work? Well, the whole transistor count was something you said something around 60,000 transistors or 64,000 transistors. Is that right?
Yeah, well, it depends how you count the ROM. If you count the ROM based on the bit locations, then it was, I think, something like 63 or 64,000 transistors. If you count if everyone is 2 bits, so as if it's 2 transistors, then you get about 75,000 transistors. And we need to remember that the 8086 was, I believe, 39,000. So it was almost double the number of transistors that were in the 8086.
Right. And so you had to, you had to do standard chip verification before you could tape out. You wanted to verify that this huge thing was going to work.
In all fairness, we did not have at the time a full chip logic simulator. Okay, I mean, you need to remember we're talking about 1979. The CAD environment was such that you had very little. A lot of it had to do with either partial simulation, like I could only simulate the data path, or I could then only simulate the micro engine, or things of that kind, and so on. And we had the large all-chip simulator that was at the level of Fortran, not at the level of gate level simulation. So, a verification. I mean, today nobody would tape out with that level of verification. They would expect much more. But in our case, that's what we could afford, and we were either lucky or skillful that it did work.
Mm-hmm. Did people have to spend a lot of time looking at those Mylar sheets to make sure that everything was as it should be?
Oh, yeah. And what we did that's an interesting thing. Actually, one of my colleagues that did not work on the project, Asher Cummington, started with this practice. When a layout person completed his piece, a certain register or a certain counter or whatever it is, he would place it on the bulletin board, and anybody who on the way to lunch or to the restrooms or whatever could stop for a couple of minutes on the board there, and if he found a mistake, he would mark it, with a sticker or something so that it will be fixed. So one of our verification schemes was simply more eyeballs looking at the thing and trying to find anything that sounded like it may need to be checked again or fixed.
Well, that's a great story. So what was it like making this decision to tape out? I mean, how were you under time pressure to tape out, or?
I don't recall us being under time pressure as far as the corporate saying, "Hey, we need the 8087. The world is waiting for it." So it was more when we believed that we exhausted our ability to perfect it or to improve it. And also, you need to understand that the best way to simulate the chip is to build it. Okay, so when we taped out, then 2 months later or whatever, we got back the silicon. Okay, then you could check how things work, and it's much easier for you to see if something doesn't work. And as I said, we were lucky that at the time, the manufacturing process already yielded us 2 working dies per wafer. Okay, so once you have a working die, you package it, you can microprobe it, you can do a lot of things with it. And this way, we had another layer of verification that helped us tremendously to perfect the product.
Do you remember when the 8087 taped out?
I think it was roughly mid 1979, so roughly June. But I must admit that my memory runs blank on exactly when it was.
Right. So what was that? So you taped out, and what happened when you got your first chips? Or your
Well,
first
we
question?
prepared, we prepared setups that you could exercise it, and besides, when you think about it, okay, well, we didn't have, we may talk later on about the first personal computer, but basically the personal computer also had in it a socket that you could plug the 8087 into and see and talk with it and do whatever. But we didn't have a personal computer at the time, so we built an emulator, something that would, again, have an 8086 in it or an 8088 in it and talk with the 8087, feed instructions into it and read from it and so on and so forth. Only it had also the ability to, microprobe and check things if in a minute you find something that doesn't work, to locate or to zoom in on where the problem lies.
Uh-huh. Where were the first 8087s fabbed?
I believe it was initially at Livermore in Fab 3, and later on it was moved to Chandler in Phoenix, Arizona in Fab 4 or Fab 6, and something like that. But it was in Western U.S.
Mm-hmm, mm-hmm. And so you fabbed them there and shipped them to Haifa and
Yes.
and worked on them there. And so, as I recall, the 8087 was delivered to was announced in was it August 1980 in the summer, just about 45 years
Yes,
ago.
well, I did the announcement actually. There was an ISSCC in San Francisco that year. I think it was in October 1979. No, so it was April 1980, something like that. And I gave the paper there. I think it also won, I don't remember, somehow I ran blank on that, that it also won the best paper award in the ISSCC at the time.
Oh, right, in San Francisco, and you had your paper on the transcendental functions. That's when that paper
the
appeared?
paper there was on the Math Processor.
Right.
The one about the transcendentals was in some Dutch paper a couple of years later.
Okay. Oh, very good, very good. Oh, so you got to announce the 8087 at ISSCC,
Yes.
which is the Solid State Circuits Conference, right? International
Yes.
conference, right?
Right.
Well, that was quite an honor to get to do that.
Yeah, well, I don't know if I appreciated it at the time. In retrospect, I think it was a tremendous honor. Yeah.
And yeah, so now let's circle back to the. So we have. So at that time, Intel had the 8086 had been out for a while, and then the 8088 that you developed in Haifa, that with the 8-bit bus, the less expensive part with the cheaper interface, was out, and now the 8087, the Math Coprocessors that would work with either of them, and what did the world think of that? so tell that good story. You had a famous first customer, early customer.
I don't know if that was the first customer, but clearly the most important one was the Boca Raton team of IBM that did the first IBM PC. Now, the interesting thing about it, and this is something that I heard from a couple of people who were on that team, the leader of the team was Don Estridge, who unfortunately passed away in a car accident about 5 years later or something like that. But they developed, actually, they kept two options open. One was with the Intel 8088, and one was with the Motorola 6800. And it was like a tie almost on between them. And I was told by a couple of people from that Boca Raton team that it was the fact that Intel had a Math Coprocessor and Motorola had nothing in that domain that tipped the scale, because they believed that the personal computer should do a lot of computations, and you can't do it if you don't have. I mean, it would be, you do it in software, would be so slow that it wasn't considered a viable solution. So that the fact that Intel had the 8087, regardless of whether on the specific PC that you ship you put it in or not, would be what determined that they would use the Intel architecture rather than a Motorola architecture. And if that is true, okay, this determined the fate of Intel for the following 30, 40 years, because ever since, remember the Intel Inside, Intel architecture. I mean, the fact that the IBM PC was what set the standard for the whole PC industry for many generations is what made Intel what Intel is, the leader of the semiconductor industry. So I'm very proud that a possibility that we did contribute that strongly for making the Intel architecture be the winner one.
Right. So just to tie that together, so the first IBM PC, was it called the 5051, model 5051 out of Boca Raton, had the 8088, which was developed in Haifa,
Right.
based on the 8086, right? And a socket. Every model had a socket for the 8087, which wasn't out in sufficient quantity and at a cost that made it possible. So you
actually, interestingly enough, some years later, I think 5 years later or so, I was the R&D manager for the how you call it, EUCD, End User Components Division, that Mike Amer ran, that was shipping 8087s to be plugged into the sockets. Okay, among other, no, it was already the 387 actually, the next generation, but basically it became a business on its own also, so that some people would buy the PC without the math processor and later on would buy in Fry's or wherever the math processor to plug into and upgrade the PC.
Yeah, that was a huge turn in Intel's business. So, what did your team do after the 8087 appeared in 1980, and what did you do next regarding the 8087? Did you shrink it?
Yes, 2 years later or so, we shrunk it 2 generations. I mean, there was a 411, which was certain geometries. Then there was 414, and then there was the 417. 417 was twice 20%. So you got overall 80 times 80%, namely 64%. So every size, every line, okay, if a line was, let's say, 10 microns, it became now 6.4 microns, and so on. So it shrunk the die size tremendously, and because of that, because instead of having 2 dice per wafer, you had something like 15 dice per wafer or 20 dice per wafer or whatever. So, but it was an optical shrink. It had nothing to do to mess around with any logic or anything, and it worked tremendously well.
Mm-hmm. That's great. Well, and the 8087 made Intel a lot of money for several years, right?
Yes, 8087 and its successor, primarily the 8387, which was the math processor for the 8386, was sometimes the most profitable product line of Intel. There were years where, if it were not for the math processors, Intel would have been roughly break even. Because of the math processors, it was tremendously profitable.
Yeah, that's great. So how about your team? Why don't you talk a little bit about what happened to all of you as
okay,
you?
As I mentioned, we had roughly 7 engineers, so it varies. For instance, Moshe Stark, who was the inventor of the 2 bits per cell ROM and so on, about half a year or a little 9 months maybe after the start of the project, he went on in order to lead the Ethernet controller, the 82586. So he became the leader of the team that did the data communication department chips in Haifa. Okay, and did very nice engineering job there. Alex Konauser, who inherited the circuit design leadership from Moshe Stark, okay, was a new immigrant from Romania, and he was a marvelous person. He grew up further, and about 10 years later, he was already the 15 years later maybe, was the general manager of Intel Israel, the design center, and went on to become the general manager of the manufacturing fabs and eventually the president of Intel in Israel. Okay, so he started his career on the 887. Unfortunately, he passed away about 3 years ago from health issues. Rafi Retter went to found a new company called Oren and did a career outside of Intel. Arik Shemer, whom you know, just is going to retire from Intel on Sunday, on August 31st, after 47 years in Intel. So he was the leader of a lot of things, especially the testing and debug and activity in Haifa, and is retiring with honor next week.
Arik started in December 1978, is that right?
I think he started earlier. I think he started in late 77, in December 77. Maybe, but I don't think it was as late as December 78, but doesn't matter.
But after 47 years, he's retiring. He started on the 887, and here he is. Okay, thank you.
Yes, definitely, he was on the team, so on. So most engineers went on to other activities and excelled there. Personally, after that, about a year later, actually on January 1981, I became the general manager of Intel in Israel, and I did it for 5 years, very rewarding years. Afterwards, I relocated to California, and I did there some corporate functions for another 3 years, and got back and did some corporate functions here, and then I moved on outside of Intel with high-tech assignments in various companies. I'm not sure we have the bandwidth to go into that detail.
We'll do that another day. But yeah, you had a long career, but you had a tremendous start leading this ambitious 8087 project, and the Intel Design Center (IDC) kept growing right after this. That you started with a very small team in 1974.
Yeah. Well, for example, when we started, we were 4 engineers. When we did the 8087, I think as a team we were something like 25 engineers or something like that. When I inherited the whole design center, we were about 100 employees, and the majority of them were engineers. And when I turned it over 5 years later, there were about 200 employees. Okay, but today there are in Intel Israel somewhere between 10 and 12,000 employees. Okay, so it grew tremendously. A lot of it due to the manufacturing fab, but also the development center has now something like 5,000 employees in it, most of them engineers. I'm very, very proud of the successes they had, most of them when I was already not involved, so I don't have a personal contribution to that, but I still observe it with a lot of pride and admiration.
Absolutely. Well, that's great. Do you have any closing thoughts?
I would say one thing just to put things in proportion. Besides the fact that it was a tremendous engineering success, it had 3 impacts that I think are important. One of them that was already mentioned is the implementation of the 754 standard, which basically impacted the whole computing industry, I would say, that today computers all around the world are more reliable and more accurate, less airplanes fall because of compute mistakes, less, mistakes in trading of, shares or in banks and you name it. Anywhere you go, anywhere there are computations being done, they are more reliable, and we are the ones that started this more reliable scheme. So I'm very, very proud of that. The second thing is the fact that Intel in Israel, okay, became one of the two leading centers of Intel in the world. Was started with the 8087. Later on, there were other teams and other very, very impressive accomplishments that reinforced that position. And the third thing is, as I mentioned, could be that IBM decided to build the IBM PC on the Intel architecture. If that is true, then the 8087 did a major contribution to the success of Intel throughout the generations. So I'm proud of all three of those, and very proud of the team, and very proud of the fact that I had the opportunity to take that challenge and beat it.
Well, that's excellent. Well, Rafi, thank you very much for taking all this time to share your story, your impressive tale. It's been great to speak with you.
Thank you, and good luck.
Okay, take care. Bye-bye.
Bye.